In this video, today we are going to discuss about Poisson's bracket and Jacobi's identity. Okay, so these are the topics we are going to discuss in this video. So what do you mean by Poisson brackets? Suppose we have two functions, and those are suppose f and g, and their functions of suppose p's and q's, pi, qi here, pi and qi. Then Poisson brackets of these two functions is given by Poisson bracket f and g. Poisson's bracket of these two functions f and g is given by summation from I del f by del qi by del g by del g by del pi minus del f by del pi del g by del qi. So given by this. Now let me tell you some important relations of Poisson brackets. So first one, Poisson bracket of function f and g, it is equal to negative of Poisson bracket g and f. Okay, g and f. So we can prove this one. To prove it, let us expand the left hand side. Okay, so Poisson bracket of f and g, that can be written as summation del f by del qi del g by del pi minus del f by del pi into del g by del qi. Okay, now if you take minus sign common, then it's gonna be, so here now this term going to be positive and it's gonna be negative, so that's why we can write del f by del pi del gi by del qi minus del fi by del qi del gi by del pi, or you can write in this way minus summation del gi by del qi del f by del pi minus del gi by del pi del f by del qi. Okay, so that means, and this is nothing but this is the expansion of this right hand side. Okay, that's why we can write this as minus Poisson bracket of g and f. So this is the right hand side. Okay, so hence proved. So we have more relations, and I'm not going to show, and I'm not going to prove all the relations, so let me write the other relations. So next relation is Poisson bracket of f and f, that's always going to be 0. Okay, that means if you have the same function here, then that's going to be 0. Number 3, and Poisson bracket of function f and a constant c, that's always going to be 0. Okay, remember where c is a constant. C is a constant. So now the next one is Poisson bracket of c into f. Here also c is a constant, f is function, and g, that's always going to be equal to, so c into Poisson bracket of f and g. Okay, now our next relation is Poisson bracket of function f n sum of two functions z1 plus z2, then it's going to be equal to Poisson bracket f n z1 plus that of f n z2. Okay, so now remember one thing, if this sign is minus, this is minus, then here we will get minus sign. Okay, remember that. Now number 6, our next relation, Poisson bracket of function f and product of two functions z1 and z2, that's going to be equal to Poisson bracket of f and z1 into z2 plus Poisson bracket of f of function z2 into z1. Okay, now our next relation is del by del t of Poisson brackets partial time derivative of the Poisson bracket f and g, that's going to be given by Poisson bracket of f and del z by del t plus del f by Poisson bracket of del f by del t and z. So let me write it properly, del t. So this is our last relation. Our next topic is Jacobi's identity. So in order to prove that identity, we are going to use some relations from here. We have to use this relation and also this relation. Okay, so we are going to use this relation and this one as well. Okay, these three relations are required to prove the Jacobi's identity. So now let us discuss about Jacobi's identity. Jacobi's identity. So what is it? Now you say, suppose we have three functions x, y and z, and they are suppose functions of p's and q's. Then the Jacobi's identity is given by Poisson brackets of x comma Poisson brackets of y and z, then plus Poisson brackets of y and that of z and x, then plus Poisson brackets of z and that of x and y, and this is equal to 0. Okay, so how to prove this identity? So let me show you how to prove this identity. So now in order to prove this, first let us take these two terms. Okay, and but here we are going to exchange or we are going to reverse the order of these two. Then what will happen? X Poisson's brackets of x and that of y and z, then now it will be minus if we interchange these two. Okay, z and x will be now x and z. Okay, x comma z here. Now we are going to expand these Poisson brackets inside the Poisson brackets. Now if you expand those Poisson brackets, then what you can have, you will get summation. So first one, del y by del qi, then del z by del pi minus, then del y by del pi, del z by del qi. Similarly, if you expanding this, we have got this. Okay, so now what we can do, we are going to apply this identity within brackets of function f n sum or difference of two functions g1 and g2, g1 minus g2 here. These are also two functions. Okay, then it can be written as within brackets of function f n g1 minus that of f n g2. Okay, so here we are going to consider this x as f and consider this part as g1 and consider this part as g2, and similarly here also this y should be considered as f, and this is as g1 and this is as g2, and applying here Poisson brackets of xn summation del y by del qi del z by del pi minus del x summation del y by del pi del z by del qi. Okay, this part is obtained from this part. Okay, similarly from this part we are going to obtain two more expressions. Those are minus Poisson brackets of yn sigma summation del x by del qi del z by del pi plus y Poisson brackets of yn summation del x by del pi del z by del qi. So this is what we have got now. So then again we are going to apply this identity f Poisson brackets of f and product of two other functions g1 and g2. So in that case it gives Poisson brackets of f and g1 into g2 plus Poisson brackets of f and g2 into g1. Okay, so what we are going to do here in this case, so here this x should be considered as f and this should be considered as g1 and this part should be considered as g2. Okay, similarly here also this is f g1 g2. Okay, and similarly here also this is f, this is g1, this is g2, and here also this is f, this is g1 and g2, and comparing with this identity we will get, let me take another page, I will write the result directly. Okay, there. So now finally we have got this. So here you can see, if you compare these two terms, here you can take z by qy common. Okay, so this is minus. If you make it negative, if you interchange the order of these two, then this sign will be negative. Okay, then we can take minus z by z qy common. Okay, if you take this common from here, then what you will get, and so let me tell you one more thing here. Okay, first let us take common this, so summation of this, then minus del z by del qi within bracket Poisson brackets of del x by del pi and y plus x and Poisson brackets of x and del y by del pi. So that is what we have got. Okay, so what we have done from these two terms, we have taken minus del z by del qy, and these terms their order is interchanged here in this case, as we have made it minus and we have taken minus common. Okay, similarly we can take del z pi, del z by del pi, and here also del z by del pi from these two terms. Okay, if you take these two common, then what will happen? Then you will get here plus del z by del pi within bracket Poisson brackets of del x by del qy and y plus Poisson brackets of x and del y by del qy. Okay, now let us write the remaining terms as they are. Okay, so this part from here to there, let me close the bracket. So from this remaining parts we have got this. Okay, from these parts we have got this, and taking these two terms common, and from here this one and this one common, we have got this result. Okay, so now what we are going to do, now let me write this result on other page. Sorry for the mistake, I have done a mistake here. That is here we should have del by del pi. Okay, now it is okay. So here you can see, and this can be written as summation del by del qy Poisson brackets of x and y in del z by del pi minus, then you can write del by del pi Poisson brackets of x and y into del z by del qy. Okay, so here you can see from this result what you can write. So this gives Poisson brackets of x and y, then Poisson bracket of x and y and z. Okay, z, and which is equal to, if you change the order of these two, then it will be minus z Poisson brackets of x and y. Okay, so this is what we have got, and our initial expression was, initially we had taken Poisson brackets of x and that of y and z minus y, this is Poisson brackets of z, x and z. Okay, so Poisson brackets of y and that of x and z. Okay, that is equal to minus what we have got now, this result. Okay, z Poisson brackets of z and that of x and y, that is what we have got. So here you see from this, let me rewrite it on another page. So you see we have got this result. So from here you can see what we can do. So we have an identity, that is del by del x of function f, Poisson brackets of function f and g, that is given by Poisson brackets of f del g by del x plus Poisson brackets of del f by del x and function g. So here you see we are going to apply this identity here. okay, and also here. Now consider that this is this part and this part is this one, okay. Then this result then can be written as, this can be written as summation I, and outside a bracket we had del z minus del z by del qi, and this part will become Poisson brackets of x and y, okay, according to this identity, okay. Similarly, applying here, if we apply this identity here, then we will get, sorry, let me clean this bracket, okay, del z by del pi del by del qi of Poisson brackets x and y, okay. So we are going to have this. Now you see this portion, if you expand and simplify these parts, these terms, then they will be cancel out each other, okay. So then remaining portion will be 0, okay. So finally we have got this result, and here you see, if you interchange the order of these two functions, then this sign will be positive, and if you bring this one, then this sign will be positive on this side, and on this side we will get 0. So that's how we can have the Jacobi's identity. Let me show you. So Poisson brackets of x and that of y and z, then so let us interchange now these two functions x and z, then here we will get positive Poisson brackets of y and that of, now it will be z and x, okay. Then this term on this side, it will be positive z Poisson brackets of z and that of x and y here, so that's going to be equal to 0 on the other side of the equal sign after shifting this term to the left side of the equal sign, okay. So this is what Jacobi's identity, okay, hence proved. So hope you have understood this. If you like the video, share with your friends and hit the thumbs up button, and please subscribe the channel and help me to grow the channel. Thank you for